Viewers, in today's class, we are going to discuss yet another important and very conceptual problem from integration, right? So, in this class, we'll solve this important integral, which is from minus infinity to infinity, and the integrand is 1 over x square plus a square whole square, right? So viewers, here in this lecture we'll solve this integral very easily by the method of substitution and by applying the properties of beta gamma functions, right? So viewers, this integral can also be solved by the method of Cauchy's residue formula, right? But here we'll restrict ourselves to the application of beta and gamma functions, and we'll take up the calculus of residues and the contour integration in our next videos, right? So let us solve this integral. So let us take this integral as I, right? And here I will make the substitution, that is x square is equal to a square t, right? So t is our new variable, right? So x can be written as a square t raised to the exponent 1 over 2. So x is a times square root of t, right? Okay, now let us differentiate x with respect to t. So we have dx over dt is equal to a being constant. So the derivative of square root of t is given by 1 over 2 times square root of t, right? So now we can write dx as a over 2 and t raised to minus half, and here we have dt, right? Okay, now see, here the limits of integration are from minus infinity to infinity, right? So here we can simplify this integral by using a property of definite integrals. That is, we can write I is equal to 2 times 0 to infinity dx over x square plus a square whole square. So here we have applied an important property of definite integrals, which says that minus a to a f of x dx is equal to 2 times 0 to a f of x dx, right? Provided this function or this integrand f of x is an even function, right? So here f of x is given by 1 over x square plus a square whole square, and we can easily see that if we replace x by minus x, then f of minus x is equal to 1 over minus x square plus a square, and here we have square. So this is 1 over minus x square is simply x square, and this is a square whole square, right? So we again get the function itself, right? So f of minus x is equal to f of x, which suggests that the integrand 1 over x square plus a square whole square is an even function. So we can apply this property. So minus a to a, here we have minus infinity to infinity. So this is 2 times 0 to a, 0 to infinity, and this function f of x, right? So now let us express this integral I in terms of the variable t, right? So we have 2 here, 0 to infinity. Now see here the limits of integration are from 0 to infinity, because when x is 0, then the value of t can be calculated from this expression. So the value of t is also 0, and when x is infinity, that is when x tends to infinity, then t also tends to infinity, right? So we have 0 to infinity. Dx can be replaced by a by 2, t raised to minus half. Here we have dt, and in the denominator we have x square. X square can be replaced by a square t plus a square, and here we have square, right? So now this 2 and this 2 get cancelled, and we can take a outside the integral. So we have 0 to infinity t raised to minus half dt, and here we can take a square common. So now when we take a square common, we get a raised to 4, right? Because here we have a square, we have whole square. So we have a square t plus 1, and here we have the whole square. So this is 4, and we have here t plus 1 square, right? So here this a and 1a get cancelled, so we are left with 1 over a cube, and we have 0 to infinity, and here we have t raised to minus half dt, and in the denominator we have t plus 1 whole square, right? So now let us rewrite this integral in terms of beta function, right? So we have I is equal to 1 over a cube, 0 to infinity. Here we have t raised to minus half, and t raised to minus half can be written as half minus 1, because half minus 1 is minus half, and t plus 1 square can be written as half plus, here we can write 3 by 2, right? And here we have dt, because half plus 3 by 2 is 2, right? 3 plus 1 is 4, 4 divided by 2 is 2. So we have expressed this integral like this, because we know that beta m comma n is given by this integral, that is 0 to infinity x raised to m minus 1 divided by x plus 1 raised to m plus n, and here we have dx, right? So if we compare this integral with this one, then the value of m is half, m is half, and here this is m, this is also m, and n is 3 by 2, right? So now this integral I can be written as 1 over a cube, and we have here beta of mn, and m is half, n is 3 by 2, so we have 1 over a cube beta of half comma 3 by 2, right? So now we have to calculate the value of beta half comma 3 by 2. So now for calculating this expression, we have another important relation, that is beta mn is given by gamma of m, gamma of n divided by gamma of m plus n, right? So beta half 3 by 2 is given by gamma of half, gamma of 3 by 2 divided by gamma of half plus 3 by 2, right? So now see, we have one important relation in gamma function, which says that gamma of n plus 1 is equal to n times gamma of n, right? So gamma of 3 by 2 can be written as gamma of half plus 1. So this is half, because n is half, so we have half times gamma of half, right? And gamma of half is square root of pi, right? Because we have gamma of half is equal to square root of pi. So here we have now 1 over a cube, and the value of this expression is gamma half. Gamma half is square root of pi, and gamma 3 by 2 is half square root of pi, and in the denominator we have gamma of 3 plus 1 4 over 2, that is gamma of 2. So now the value of gamma of 2 is 1, right? Because we know that gamma of n plus 1 is equal to n factorial, right? So gamma of 2 can be written as 1 plus 1, so that is 1 factorial, and 1 factorial is equal to 1, right? So now we have 1 over a cube, and this is half times the square root of pi times the square root of pi, so this is pi over 2, and gamma of 2 is 1, right? So the value of this integral can now be written as pi divided by 2a cube, right? So here's the value of this integral is pi over 2 times a cube.